So this is something called the reaction quotient, and it's and factors that affect equilibrium. All right, so let's see if I can't get rid of some of these buttons. That might help me a little bit out. If not, we'll see what happens. All right, here we go. So you saw something like this yesterday, equilibrium calculations, and we tried to figure out, what is the Kc value for this reaction? Remember, Kc being the equilibrium constant. So you did something maybe that looked a little bit like this. So we had Kc equals, and whatever the concentration of C was, and then we put in D squared. That was the products here. And then we're going to divide it by the reactants. So we got a concentration of A, and then B squared. Sorry, it's a B there. And we're assuming that these are all gases, A, B, C, and D, or we're assuming that they are aqueous. Now, it wouldn't make sense to have a molarity listed here if they weren't a gas or an aqueous thing. Okay, so that part does have to happen. Remember, we don't put solids or liquids inside the equilibrium expression. So hopefully you saw this. We plugged in values and so on. Okay, well, it says at equilibrium, these are the values. And we could plug them in and solve for what K is if they were at equilibrium. But if instead it didn't say equilibrium, let's cross this off. I'm going to switch to red. Let's cross that off. And let's say it said initially, implying that we are not at equilibrium. This comes up with something called the reaction quotient. And for some reason, this gets to be a really confusing thing. But if you understood how to get Kc and all that, you understand how to get the reaction quotient. It's actually the exact same thing. The only difference is the reaction quotient occurs when we're not at equilibrium. At equilibrium, then we have the reaction constant. Let me tell you what I mean, okay? So let's just say those values that are listed there are not actually equilibrium concentrations. Let's just say we throw all these concentrations in the flask. We haven't even let the thing go. We freeze time. We're at time equals 0, let's say. So we're not at equilibrium at all. Well, this reaction quotient Q is going to equal to the exact same thing that you see right here. So I could plug in my values, 0.2, and then this was 0.25 squared for D, and then we had 0.1 on the bottom, and we had 0.05 squared. If my memory serves me right, I'm not doing a calculator, so forgive me if I get the answer wrong. I believe this was 50. I'm just trying to think from a couple days ago when we last went through this. So you may think, well, what's the difference? I mean, okay, the idea here is what someone might want to do is if we know what the equilibrium constant is, Kc, and we know what values we're starting with, we can use this reaction quotient to predict, is the reaction going to start, with, it's backwards here, isn't it? Is it going to start more with this C and D side and then go the reverse reaction first and create more reactants, breaking down the products? Or based on the quotient and compare it and seeing how it compares to Kc, the equilibrium constant, are more reactants going to react in the forward direction for a while and make more products and less of these? And then it always goes to equilibrium. Okay, the reaction will eventually go to equilibrium, but at this point right now in time, it is not at equilibrium, so what we use is the reaction quotient. Hopefully, as we go through this, will make a little bit more sense maybe here. All right, here we go. So you can see reaction quotient. It has the exact same expression as Kc would be. You've got the reactants over the products. And then you've got some numbers here and so on, some values. And you can memorize this stuff. Use this maybe to help you when you're figuring out. Keep in mind, this is really probably the big thing here. Where's my highlighter? They took away the highlighter on presenter mode? Oh, I can't do that. I have to go to standard. All right. This is the big thing right here. The reaction will go until the quotient equals the equilibrium constant. When that happens, we are at equilibrium. So let me just make up some numbers here. Let's just move this over to the side a little bit. All right, let's go with blue here, and let's say that the equilibrium constant for that reaction, and I don't know this, I'm just making up a number. We're going to make up some nice numbers. Let's just say that it's 100. So this is very, very product favoring. It's going to want to mainly be in the N2O4 side and less on the NO2 side. All right. So, and I decide, you know what, I want to start this reaction. when you start it, chances are it's likely not going to be at equilibrium. So I'm going to start this such that my initial N2O4 concentration, let's just make it be 1 molar. And let's just make things easier, let's make my initial NO2 concentration to be 1 molar. So when I throw those into the flask at time 0, it's not at equilibrium. So I can plug these things in and see what I get for answer. Well, Q is going to equal 1 over 1 squared, and it equals 1 at this point in time, right? I'm just plugging in numbers to this thing right here. Okay, so this is what I end up getting. That would be at the start of my particular reaction doing this now. And if I'm thinking, which way is this thing going to shift? Which way is this going to go? Right now my quotient's at 1. I know it's not at equilibrium. I know the equilibrium constant here is 100. Now you can use these things that are on the side. I personally don't remember those and don't like to use those. I think of it this way. I know that this reaction is going to go such that this 1 is going to, you're going to change the values of these things. Their concentrations are going to change as the reaction's proceeding. I know that this 1's eventually going to turn into 100. How does it do that? It goes up by making the numerator bigger and by making the denominator smaller. As the numerator gets bigger, that favors a bigger number overall here. And as you divide by smaller and smaller numbers, that also favors this number getting bigger. So since I know my product number is going to get bigger and my reactant number is going to get smaller, that means my reaction, if this were the case, is going to shift. It's going to shift to the right. I'm going to get more reactants produced. So this is going to eventually end up being down. It's going to be less than 1 molar at whatever equilibrium is. And this is going to be greater than 1 molar once this thing finally hits equilibrium. So that's all this is. The quotient and the reaction rate constant, I don't want to say they're exactly the same, but if you think like, wow, these really look like they're the same thing, you're probably on the right track. Now let me just change this up. Let's say instead this Kc is not 100. Let's say instead this Kc, let's go with 0.01 instead. Let's say I start again with the exact same concentration. So at time 0, I start with 1 molar each. You plug them in, okay, we got the 1 divided by 1 squared. I get a reaction quotient at time 0 for me as being 1. Remember, the reaction is always going to want to turn into, that's always going to go towards the actual equilibrium constant, whatever that is. So, well, right now I'm greater than that equilibrium constant. The reaction is going to proceed to make this smaller. So how do you make numbers smaller? Well, you make the numerator smaller. That's one way to do it. And you also divide by larger numbers. So that means this is going to go down, which is the product number. This is going to go up, which is the reactant number. This reaction is going to shift from right over to left, and it's going to keep doing that until eventually this number hits 0.01, the equilibrium constant, and then it's going to stop. Reaction doesn't really stop, right? But the net change is going to stop. It's going to be at equilibrium at this point, all right? And so that's how this works. That's how we can use this. All right, let's move on. So here you go. Here's a reaction quotient problem, okay? Throw out all the Kc value and stuff that I used before. The concentrations of the flask are such and such. Which way will this reaction shift to reach equilibrium? Pause right now. See if you can solve it. Go back and look and see what I went through. When you do, I'll be here and I'll go through the answer. All right, I hope you paused. I hope you tried it out because we're going to try it. Let's figure out what we got. I'm going to first plug in these values inside my reaction quotient / pseudo equilibrium, whatever you want to refer to it as, expression here. Okay, so the top number, 0.025. The bottom number for NO2 is 0.015. I do have to remember to square it. So let's see what my reaction quotient is. I'm going to pause the video because I feel like using a calculator real quick. Alright, I used my calculator. I found out that this is equal to roughly about 111. So if we take a look at it, my quotient tells me where I'm at right now in my progress to getting towards equilibrium in the reaction. I'm at 111. I'm going to keep going until that number reaches up to 170, the equilibrium constant, and then it's going to hit equilibrium. So this number needs to get bigger. How does it do that? The numerator is going to get bigger. The denominator is going to get smaller. We want to divide by smaller numbers to make this overall quotient bigger until it eventually hits equilibrium, which is Kc. That means we are going to shift to the product side to make the product number bigger and the reactant number smaller. So which way will it shift? It'll go to the right, or to the products. Okay, here's another quotient problem. If you want to look at this, go ahead, pause it, and see if you get the right answer. I'll just tell you what I get here. Okay, did you pause? I hope you did. Here we go. This one here, let's take a look. Let me get my quotient expression. So I'll switch to blue. All right, so Q is going to equal the NO concentration, and that's going to be squared. And then I'm going to divide that by N2, and then I'm also dividing it by O2. Plugging in numbers, 4.2 times 10 to the minus 3 on top. I have to make sure that gets squared. And on the bottom, it looks like I have 0.5. And it looks like I also have 0.25. Let me pause the video while I type this in my calculator for a second. Okay, so it looks like I'm getting a value here that's approximately equal to 1.41 times 10 to the minus, looks like 4. So we take a look at it. Here's where I'm at right now with the reaction quotient, 1.41 times 10 to the minus 4. I am not quite at equilibrium yet. This is a bigger number than this. So I need to make this side bigger, the products, and that means the numerator is going to get a little bit smaller, and this one is going to also shift to the right, or the product side. Now, it's almost there, right? It's not, you're looking at it, it's a very small number. Well, look at Kc's magnitude. It's much less than 1. It's going to be definitely a more reactant favoring reaction. These numbers, 0.5 and 0.25, really aren't going to change much as this proceeds. This thing here, yeah, it'll get a little bigger, but it's getting there, so it's not going to go too much farther likely. All right, shifting gears now onto something else. It's called Le Chatelier's principle. This is a little bit more qualitative of a concept. Basically, here's the idea. A system hits equilibrium. It's got the forward reaction, the reverse reaction. They're doing the exact same thing rate-wise. It's looking like there's no change. There's no net change with time, in other words. And then you go ahead and you do something to make it mad. You make a change. Maybe you warm it up. Maybe you add a reactant. Maybe you add a product. You take away a reactant, whatever. Change the pressure or something. It gets mad. It doesn't like that. And so it's always going to try to do something to minimize the change that you did. All right? So I'm going to take you through a couple concentrations or a couple scenarios here. See the best I can to show you like a little bit of a video here of how these things might work. And yeah, we'll go from there. Pardon the message there. Okay, so anyway, let's take the first scenario. Changes in concentration. So here's the idea. If I've got a reaction, it's in a closed container, let's say it's at equilibrium now, everything's fine, and I do something to make it mad, it's going to always want to do the opposite. Just think, have you ever done that? Someone does something like, no, I'm mad at you. I don't like that. I'm going to do the opposite just to make you mad now. All right, so here's the idea. If I add more SO2 at equilibrium, well, it wants to get rid of the SO2 as best it can that you got rid of it. The reaction doesn't have magical hands. It can't just open its own container and let out the SO2 that you added to it. But what it can do is it can try to react it away as best it can. So if I add SO2, it's going to want to shift to the opposite side and make more SO3, removing that SO2 as much as it can that you added. And as kind of a side effect, the O2 is also going to go down and get removed and react with some of this. If instead I add SO3, well, it doesn't like that at equilibrium if you do that. So it's going to try to minimize your adding of this SO3. So it's going to try to take that away by reacting it in the reverse reaction, making this go down a little bit after your addition and making the oxygen and the SO2 increase. Okay? And you can imagine if I've got this at equilibrium and I remove SO3, it's going to get mad that you removed its SO3. It wants to replace it. So it's going to react more SO2 and O2, so these are going to decrease a little bit. And then this is going to increase after you've removed it. to try to replace as best it can what you removed. That's kind of how this stuff works. And so let me see if I can't show you a video here where they do something like this with concentration. So here is a reaction. I've got it muted, this video muted, so you can't really hear the narration. But I'll just tell you, they got these beakers here so you can kind of see what they look like. I thought they did a pretty good job here with what they're doing. Equilibrium, kind of in the center position. I mean, they're all at equilibriums, but they've set this middle one so you can really see the center position. You know, if we're shifted far to the left side, it looks pink. If we're shifting far to the right side of this reaction, it looks blue. They're all at equilibrium technically here, but they've made it such that the middle one is kind of the middle. Purple, in this case, is kind of the middle of pink and blue for this reaction. And I believe what they are going to do first is they're going to add hydrochloric acid, which adds Cl- to this. So think about if I add Cl- here, which way is this going to shift? Is it going to shift to the right and make it look more blue? Or is it going to shift to the left and make it look more pink? So let's see if they do that here. I believe it was hydrochloric acid. There it goes. They're adding more of that, and you can see you're adding a lot of chloride ions that are in the hydrochloric acid, and now it has tried to minimize you adding that, so both of these react away a little bit, and it forms more of this. And there's actually more water in there, which we obviously can't see because it's clear. Now, I think what they're going to do here, if I can find it, if I can fast forward to the right spot, is what they're going to do is they're just going to take a beaker of water and start pouring it back in here. So think about what's going to happen if they add more water to this. Right? So water is on the right side of this reaction. It's at equilibrium now. It's happy again. Don't make it mad. Well, that's what we're going to do. We're going to add water. So think about which way this would shift if we add some of a product in this case. It's going to want to try to then immediately remove that water. It does it by decreasing this, decreasing some of this, and creating more of these things. We should see this turn a little bit more pink. All right, I believe the water is coming here any second now. Here it comes. And you can see it on the side there, and they mix it around. And there you go. Now it has shifted more to the left and made it pink. So that's how that can work. All right, that's changing in concentration. Okay, moving on, changes in pressure. This one's a little trickier to show maybe with some videos, but I believe that I have one. Here's the idea. Same thing with changes in pressure. You increase the pressure. Typically, you increase the pressure maybe by decreasing volume. Remember, pressure and volume are opposite. They are, inversely proportional. So, when you increase the pressure, well, it wants to decrease the pressure, okay? It can do that by removing gas. Now, it can't, just think about like you squeeze on a balloon, you're increasing the pressure. Well, the air inside can't open the balloon and let itself out. It doesn't have hands again, but it can shift the reaction whichever way. So it always sort of shifts to the lower moles of gas when you increase the pressure. You increase pressure, it's like, I want to bring my pressure back down. I'm going to just go to lower moles of gas because it's like letting air out of the balloon. That's going to go to lower pressure. All right, so let's take a look at some of these reactions that I have that are sitting here. For gas reactions, it says, which of the following would an increase in pressure due to the following equilibrium? So assuming all 1 through 4 of these are at equilibrium, what sort of things would happen? So let's take a look. We're going to look at the moles of gas, and let's get rid of this. We don't need this stuff here. Okay, so taking a look at it, there are 2 plus 1, 3 moles of gas on the left side, 2 moles of gas on that side. Well, increasing the pressure, it wants to let moles of gas out so it can bring that pressure back down. We shift to less moles of gas. So this one, increasing the pressure, would shift it to the right. Hopefully you are able to use intuition and think, what would happen if I decrease the pressure of that one? Well, it would just do the opposite because it would want to bring its pressure back up. All right, let's take a look at number 2. Increase of pressure. 2 moles of gas on the left side. Here we've got 1 plus 3. 4 moles of gas on the right side. Increase of pressure always shifts to less moles of gas. And there we go. We go to the reactant side this time, shifting to the left. All right, think about what you'd have for number 3. Pause. Because here it comes. What would we do? This one's a little tricky. 0 moles of gas on the left side. Solids and liquids are not gases. 1 mole of gas on the right. If this was truly at equilibrium, it's a little bit fabricated, don't worry about it. It would shift to the left. to the side that has less moles of gas. All right, and then the last one, number 4, think about what you got for that. Pause, because here it comes. Here comes number 4. We've got 2 moles of gas on the left. We've got 2 moles of gas on the right. What would an increase in pressure do? It would do absolutely nothing. Not when you got equal moles of gas on both sides. And that is it. All right, moving on to temperature. I'll see if I can't maybe show you a little bit of a video for this one. It's that same cobalt chloride one that we looked at a video for just a little bit ago. But all right, anyway, this one's a little trickier. Okay, temperature, this is a very important thing. IB hammers on this a lot. When you change the temperature, you know, it's going to change equilibrium position a little bit too, but this is the only one that changes the value of the equilibrium constant. So just keep that in mind. Changing pressure, changing the concentration, those things are not going to change the value of Kc. Temperature does. So just keep that in mind. Now to make this work, we have to know whether or not something is an exothermic or endothermic reaction. So you can see the way I have number 1 and 2 written here. I like to write them in there, so I'm thinking of heat being on whatever side. In fact, I'm going to ignore that 50. I don't care about that. I'm just going to write the word heat wherever I see that, you know, because that's really what I think about. So just like in number 1, if I was to add N2O4 on the right side, it's going to shift this to the left. If I add heat to this reaction, it's like adding something on the right side, it would also shift this to the left. Number 2, this is an endothermic reaction. If I added heat as a reactant, you know, if I added N2 or O2, sorry, as a reactant, this would shift to the right. So if I add heat, it's going to go to the right and make more products. Now, on number 2, if I remove the heat, it's the same effect as removing N2 or O2. This acts just like a reactant in this case. Then it would shift to the left to replace that heat that I removed. The other thing to keep in mind is don't forget what your signs would be. Delta H in this case would be negative 50 kilojoules per mole. And on this one, delta H would equal positive 120 kilojoules per mole. So keep that in mind when you see those signs. All right, let's take a look and see if I can't get a video for this one. No, I'm not trying to do VRBO stuff. Okay, here we go. This is that cobalt chloride one. And it looks like number 1 is like kind of the starter color they're used to. Number 4 really is pretty much the same thing. It's at room temperature. And they're going to sort of put it in a water bath with different temperatures here. By the way, this is an endothermic reaction. So the heat is on the left. Heat is going to act like a reactant here. So if I add something on the left, it shifts to the right. So this water is fairly warm. They're adding a reactant. They're adding heat. We should see this shift to the right and make less of the pink stuff and more of the blue stuff here. And it looks like it takes a little time. They might have to swirl this around. Kind of wish they'd maybe speed it up in real time or double time or something like that. But you can definitely see as this reaction is warming up, as it's taking on heat, it is definitely shifting to the right. Okay, so we've seen enough of that. I think they're going to add ice here. Maybe I can fast forward it a little bit. They sort of swirled it around. Okay, so there's that same one, and let's put it in. Now it's like ice bath. So you can see the temperature is pretty cold, about 9 degrees, 9.5 degrees Celsius. So they are going to put this into ice bath, and now we're removing this heat. Remember the heat's here, this endothermic reaction? We're taking away that reactant. So it should break this apart and shift to the left, and you can see it's definitely becoming pinker and pinker and pinker as it is sitting in the colder water, the colder ice bath. Okay, I'm going to pause it there and just head back to what we were doing. Last one of these things is catalyst. This is a big IB question here. Effect, adding catalyst, what would that do to the equilibrium constant? And the answer is it does nothing because it speeds up. Remember these diagrams from last year? When you add a catalyst, you've created a new path, a new activation energy. It's lowered the activation energy of there. So the forward reaction definitely speeds up. And we see that very easily in open reactions, where pretty much the reaction is forced to go to the products. Well, this is a closed reaction. There's no thing that says that the reverse reaction can't take the same path. And so it typically speeds up both forward and backwards, and you don't see any effect on equilibrium by adding a catalyst. Watch out for trick questions like that. Okay, I want you to pause here and think, what are the ways that you could make this reaction produce more product? Or in other words, shift to the right. Pause it. I'm going to now tell you what the answers are. Did you pause? Okay, here comes the answers. Let's see if you can get it. To make it shift to the right, we could add more SO2. That's one way. We could add more O2. That's a second way. We could remove the SO3. I know it's a closed reaction, but we could try to somehow remove it. And that would make it shift to the right some more. Heat is a product in this case. In this case, we'd see delta H equals negative 30 kilojoules per mole because it's exothermic. It's sort of given off in the forward reaction. So I could cool this down or remove the heat. Cooling it down, lower the temperature. If you said something like that, all that would work. Okay, and the last one that I could think of here is that this is a gas phase reaction. I've got 3 moles of gas on the left, but only 2 moles of gas on the right. The other thing that we could do here is that we could increase the pressure, and that would be another method to make this work. Okay, so here's a chart here, and you can pause this and try to fill this in and think what the answers would be. I'm just going to pause it, fill in the answers off camera here, and then so you can see the answers. So let me pause the video now. Okay, so here's my notation. An up arrow means that thing is going to increase. My down arrow means that thing's going to decrease. The rows that I would really draw your attention to that tend to be the trickiest, of course, are the pressure ones and the temperature ones. I've put some NAs in some of the concentration ones just because I find students often get confused. If you're increasing B, how come it would then decrease again? Okay, well, that sometimes gets a little confusing. Yeah, you're adding B in here, but then the instant you do, it's going to, from that amount you added, it's going to try to react a little bit of it away to shift back to equilibrium. So that we don't get confused on that, that's why I put the NA in that case. So, all right, hopefully your answers matched mine. That means either, one of us is wrong if they don't match. So, good luck with this stuff.